Can anyone just confirm?
Yes, you're audible.
Okay. I hope my screen is also visible. Okay. So let's start the discussion of problem solving with STL containers and data structures. So the first thing that we will be discussing today is the concept of frequency map. So for the purpose of starting out easy, we will be just discussing this easy version of the problem. So you're given n integers a1 through an, and then you need to print all the distinct integers appearing and the number of times they are appearing. So for example, if you have something like 1, 2, 3, 7, 3, 9, 2, so you will be reporting it in some way like 1 comma 1, 2 comma 2, 3 comma 2, 7 comma 1, 9 comma 1. This means that the number 1 occurs once, the number 2 occurs twice, number 3 occurs twice, the number 7 occurs once, the number 9 occurs once. So is the problem statement clear? I hope the problem statement is clear. So this is the first set of constraints. The number of elements will be from 1 to 2 into 10 to the 5, whereas the elements themselves will be from a small range of 1 to 1. So any solutions that anyone of you might suggest?
Be done using O of n, big of n.
Big of n, and the solution is?
Using map means map of let's say x plus plus means while taking input I am increasing the frequency.
Okay, yeah. So you have actually solved the harder version. So basically, in this case, you don't need a map. You can basically have int frequency of 1001 maybe, and then for I from 1 to 1001, you set frequency of I to be 0, and then for I from 1 to n, CIN may be x, and then frequency of x will be increased by 1, right? So this is what you were saying, right? Except of using the array of integers, you were using a map from it to it, right?
Yeah.
Okay, yeah. So for this problem, where the numbers are from 1 to 10 to the 3, or anything that you can support memory of, this solution works. But as you can see that this range might be a larger. So for example, in the next version, the range is from 1 to 10 to the 18. So here, as one of you suggested, we can keep map of long to int. This, let's call it frequency as before. Then for int I equal to 1 to n maybe. CIN x frequency x plus plus, right? So what will be the complexity of this? Can anyone say? Order of
n
log n, right?
Yeah.
Because accessing a map is order log n. So this operation is order log n. And then you print it as usual. So this is a pretty easy thing to do. Okay. So now moving on to the next version of the same problem. So you have this problem from ICPC 2019 online round. online mode. So the problem here is you are given a set of strings along with a Boolean value. So you have something like ABC, 0 ABC, 1 ABC, 0 ABC, 0 EFG, 1 EFG, 0 EFG, 0 CC, C, 1. Now the thing is, the problem says that these individual pairs of integers and a Boolean value signify that this string is a spam word or not. So if something like string comma string space 1 is given, this means that this string is a spam word. Otherwise, if something like string comma 0 is given, then this means that this string is not a spam word. Now what you're asked to do is basically select the maximum size subset among these pairs such that there are no contradictions. And what do I mean by contradictions? That is, you don't have something like ABC0 as well as ABC1 in your set. That means like this signifies that ABC is a spam word. This signifies that ABC is not a spam word, but this signifies that ABC is a spam word. So this creates a contradiction. So you are allowed to have as many ABC0 pairs as possible, or you are allowed to have as many ABC1 pairs as possible, but you cannot have both occurring at least once. So is the problem statement clear? Anyone? Is there a problem with the statement?
Can you please explain once?
Okay. So basically over here what you can do is you can choose this, you can choose this, you can choose this, and you can choose this. So what happens is you are given something like ABC, you have something like ABC0, ABC0, EFG1, CCC1. So this is a valid subset of the given pairs. Why? Because there are no contradiction. And what do I mean by no contradiction? There are no things such that you are given a string x, comma 0 is also present, and x and 1 is also present. So here you have ABC0 is present, then you cannot have ABC1 present in the set. And if EFG1 is present, then you cannot have EFG0 present in the same subset. So for example, if I choose this, then what happens is ABC0, ABC1, EFG0, EFG0, CCC1. Now what happens is that you see that this is chosen as well as this is also chosen. But these two give you a contradiction because ABC0 is chosen must imply that ABC1 can never be chosen. So you can either choose ABC1 or you can either choose ABC0. So do you understand it now?
Yeah.
And now the problem asks you to find the maximum size subset that you can choose. So how do you solve the problem? Okay, so
We can keep a record of the number of times the string comes as boolean value 0 and it comes as boolean value 1, and then we select the maximum among the two, and we do the same thing for the other strings.
exactly that will solve the problem. So I forgot to mention the constraints for this problem. So the constraints are n is less than equal to 25,000. That was one, and the string size. So I think the string size is denoted by this. This is at most 5 characters. So now what you can do is you can basically come up with a solution using the same idea of frequency lamp. So instead of the traditional way of using frequency map over array of integers or long ends, here you will be using it over strings. So you can have maps like this, string comma int. Then you can have, let's say, a map for 0 and another map for 1. Okay, let's just write 0 and 1. And then maybe you can also store a set of strings that you have seen so far. And then let's say for I equal to 1, I is less than equal to 10 plus I, use string w to take in the string, and then you have another Boolean value, right? So let's just call it. Now you can just do something like 1 of w plus plus and 0, otherwise 0 of w plus plus. So I hope everyone is familiar with this syntax of ternary operators. So basically, if this value is 1, I'm keeping a count of this value. So I'm keeping a count of how many times this value occurs as 1 for this particular string that I've taken input for. Otherwise, if this value is 0, I do the same thing for 0. And now maybe I want to keep a set of all strings that I've seen. S.insert w. And then I can just iterate over all the strings and get this up. So int max size equal to 0 for string w in s, max size plus equal to max of 1 and 0 of w. I think what I'm trying to write, we store a map of how many times a particular string appears with a 0 and how many times a particular string appears as 1. So you will have something like 0 of ABC appears as 0, 1, 2, 3 times, whereas 1 of ABC appears only once, and then same for EFG. 0 of EFG appears twice. 1 of EFG appears once. 1 of CCC appears once. So by choosing the maximum of these two, you get 3. Choosing the maximum of these two, you get 2. And choosing the maximum of this and the 0 of this thing. So I guess all of you know that when a particular value of a map is not defined yet, it is by default set to 0. So this will be 1. So that means you can have a set of 6 numbers over here. So you can check this by just selecting whatever you are choosing over here. So you are choosing the 0 of ABC. So you 0 twice, then you choose 0 twice again, and then you choose 1 over CCC once. So this is the subset of 6 that you want. I hope this part is clear. So is there any doubt regarding this, whatever I discussed up to now? Okay, I hope everything is clear. And I have kept an exercise problem for all of you if you want to solve this thing. Okay. So I think you can go over this problem later on. Okay, I'll be moving on to the next topic. By the way, this part is clear, right? Is there any problem over this part? I hope it's clear. Okay, so for the next problem that we will be discussing, this is a very classical problem, next iter element. By the way, has anyone heard about next iter element or monotonic stack? Can everyone who have heard about this raise their hands? Okay. Okay, so this will be a new topic. Well, let's jump into the problem statement first. So you are given n integers, a1 through an, and now you need to find for all I the smallest index j such that j appears after I and aj is strictly greater than ai. So in other words, for all integers in this particular array, you need to find the next integer that is greater than this particular array. So for example, in this problem, let's just mark the indices for this. So for example, the next greater element of this thing occurs at the second index. This is this particular index. For this thing occurs just after this. For this 8 occurs over here, right? So this is the 8th index. For the 4th index, the next greater element occurs over here. For the 5th element, the next greater element also occurs at index 8, and so on. So for this will be 7 because next greater element occurs over here for here. And now when there is no next greater element, so for example, for this particular value, all elements over here are like less than or equal to this particular value. So you will just report -1. And this can go on. 11, -1, -1, 14, -1. So is the problem statement clear, everyone? I hope it's clear. Like, can someone please confirm if it's clear or there are some ambiguity in the problem statement?
Can you please say that how is the 238 coming?
Which part?
Means the last manipulation that you did.
This part.
EL what?
Okay, so this is the index of the next index of the next greater element. Next greater element.
Okay, fine.
So what is the next greater element of this element? This is this particular element which occurs at index 2. So you're writing this index 2. What is the next greater element for let's say this particular element? The next greater element for this particular element occurs over here, which has an index of 8. So you are right. It's clear, right?
Yes.
Okay. So now just to understand the problem here, can someone just tell me the brute force solution to this particular problem? The first solution that comes to mind.
We go of n square approach, we can iterate on 2 times.
So that is like for I from 1 to n, for j from I plus 1 to n, you can do something like a j is greater than ai, and this is the particular element, print j, right? And break, or maybe you want to keep some other boolean value which will tell you if you did find such an element, and if you didn't find an element, then you are going to print if not found, then you are going to print -1, right?
Yeah.
This part is clear? Okay. Now let's move on to the approach that uses a set to solve this problem. Okay, so this is a bit tricky approach. Okay, I think I can copy the entire thing, can I? Okay, let's copy this, then copy this. Okay, now the approach using sets is a bit unorthodox in some sense. So basically, what we will be doing is, so let me just tell you guys the solution to this problem, and then I'll try to convince you why the solution is correct. So basically, first of all, you store all elements in this form minus ai comma I. So a vector of the pair of the negated values comma the indices. So let's call this vector v, and then you sort this vector. Sort. So what does it do, anyone? It sorts the given sequence in decreasing order, and if there is a tie, it brings the values that come to the left hand side before the values that come to the right hand side, right? So for example, you will have -9 comma 8 as the first element, then you will have -8 comma 3, then -8 comma 5, then -8 comma 11, something like this. Then you will have -7 comma 7, and so on. -7 comma 12, -6 comma 14. So this part is clear, right? So what this does is basically sort in decreasing order. If there is a type, prefer the leftmost element. Prefer the element that comes to the left. So basically, this element is preferred before this. This element is preferred before this. That's it. Now what you can do is, now let's keep let's keep a set of integers. So basically, this will be a set of indices. This will be a set of indices. What this does will be clear in a moment. Now you iterate over v. So what you do? Let's say you have some I from, like, for I from 0 to n minus 1. For such an element, you will just add vi dot second to this particular set s. Dot insert. Let's write this a bit clearly. Insert v of I dot second. Now you check for the upper bound of this particular value. Equal to, so everyone remembers what upper bound is, I guess, for a set. And then just check if this thing is equal to s dot n. Then you just update the next of this particular element to, or maybe I can write it this way. Next of, so this will be our answer, nxt of this thing, equal to it equal to s dot n question mark. So if this is s dot n, then there is no other element. Otherwise, this will be it dot second, or maybe just the value of it, because this is the set. Okay, so I'm sure this is a bit confusing for all of you. Let me just tell you guys what's happening over here. So first of all, you have sorted this in a decreasing order, and whenever there is a tile, you just consider the leftmost element first. Now, what you do is you keep a set. So let's say you have some set over here, which is initially empty. So this will be our set S. I hope everything's clear up to these 2 points. Now, basically what we are doing, we are iterating over all elements over V. And then we are inserting the second attribute of each of these elements. So what is the second attribute of each of these elements? Well, these are the indices of the values, right? So 9 occurs at index 8, 8 occurs at index 3, 8 also occurs at index 5, those things. So what you do is you insert this particular index to your set. Well, so I'll insert 8 over here, and then I'll check what is the upper bound of this value. So what do you mean by upper bound, anyone? This was covered in the STL Containers class. Okay, so upper bound will give you the element that is that occurs in the set which has the value just greater than this particular value. So for a set 1, 2, 3, 4, 10, 20. So the upper bound of 5 is 10, the upper bound of 3 is 4, and so on. So what is the upper bound of this 8 in this particular set? Well, there is no such element that is greater than 8 in this particular set. This means the upper bound will give s dot end as its return. Now this means that you are going to assign this value as -1. So what does this mean? This means that there is no element to the right of this particular value that has a greater value than 9. So you will just mark this -1. Now the thing is, this element stays in the set. Now let's see what happens. Now this element comes next. So you have this element. You insert this particular value in the set, and then you search for the upper bound of 3. Well, now the upper bound of 3 is 8, as 8 is the greater 8 is greater than 3, and 8 is the only element that is greater than 3 in the entire set. So basically what this means is that you have seen some value to the right of this thing which is greater than this particular. So what do you do then? You just write down the value that you got when you have queried for this upper bound. So for this particular instance, you got this value 8 for upper bound. So the next element, the next greater element for this particular pair would be 8. And this thing goes on. So instead of writing this as 3, 8, let's write this. Instead of writing as 8, 3, let's just write it as 3, 8. Next comes this particular value. Then you put 5 over here. The upper bound of 5 is 8. hence you keep 8 over here. Then comes this value, so 11 is inserted. The upper bound of 11 well does not exist, hence this will be minus 1. Then comes this 7, so the upper bound of 7 would be 8. This value would be 8. And similarly this goes on. So this will be 12, this will be minus 1, then you have this 6, 14. So 14 does not have an upper bound, so this will be minus 1. And then we'll go over here, this will have 3, so this will be 2, the upper bound of 2 will be 3, hence this is 3, and so on. Is this approach clear, and why this works is clear?
Yes. Yeah.
Okay. Okay, so this particular algorithm. Okay, so can anyone tell me the complexity of this particular algorithm? Just have a look.
N log n.
So where do I write it? Okay. So this particular algorithm would take n log n time. So this is a much better solution compared to the brute force. But there is yet another solution which is even better than this already. Well, let's just, I don't need this page anymore. So this solution uses a stack. I can copy. Let's just write the indices again. Okay. Now for this solution that uses a stack, we'll be doing the following. So first of all, we will be maintaining a stack that contains some of these elements, and then we will push and pop the elements in the stack following some particular rules. Okay. So how does this work? So again, and then I'll try to explain this. For I from 1 to n, so you have a stack of, let's say, pair of incoming, long comment. So this will be a stack of value comma index pair. Now what you can do is the following. While the stack is not empty and the top value of the stack is greater than the current element, you assign the next greater integer of the stack top as the current element, and you pop the stack top. And after you have finished popping, you push the current pair. So that is the current value comma current index. Okay, let's just paste this over here. So this is the solution that we would be. Okay, now I'll be explaining what this does and why this is correct. So now what you will be doing is you will be maintaining a stack. In this stack, you will be maintaining value comma index pairs. Okay. So the first thing that you will be pushing is the first pair. So this will be 4 comma 1. Now the next value is 5 comma 2, right? Now observe that this 4 is less than 5 and there are no other elements in between 4 and 5 that is strictly greater than 4, since there are no elements between 4 or 5. So the algorithm says us to pop this particular value. So you pop 4 comma 5 1. So the current element, the current pair you have is 5 comma 2. You set next of this as I and you push this particular pair inside. So 5 comma 2. So our I is here and we have completed the entire loop of this, the entire run of one particular run of the loop. Next, our I moves over here. Now our current pair is 8 comma 3, right? Now what we do is we check if the stack is empty and the topmost element of the stack is greater than AI. So the topmost, okay, so I think this should be less than, yeah. So if the topmost element is less than AI, then we assign the next greater element of that topmost element of the stack as the current index and we pop the element. So the next greater element of the top of the stack is assigned as the current index. So this will be assigned as 3 and we pop this element. And after this ends, we will push this element to the stack. Okay. So far it seems that things are working out maybe coincidentally, but let's run it further. Now I becomes equal to 4. The current element is 2 comma 4. Now observe that 2 is not greater than the stack top. So you do not do this. You just push this 2 comma 4 to the stack top. Now you observe that you are having, okay, so now you increase I by 1 so that I is equal to 5. The current element becomes 8 comma 5. And now this element is indeed greater than this element. So you update the next of this particular element as I and then pop this thing. Now you check the stack top is, if it's greater than this element, you see that no, this is not greater than this element. So you do nothing and you push this particular value. The next element is 6 comma 5, sorry, 5 comma 6. You see that the stack top is not greater than this element, is not less than this element. So you simply push this element and move on. Now over here you see that the current element is 7 comma 7, which is indeed greater than this element. So you put this element. So the top element was 5 comma 6. So you assign the next greater element of the 6th index as I. So this is 7. And you pop this element. Now you check whether this is less than this particular element. You see no. So you simply push this element. Now you move on to the next particular value. So this is 9 comma 8, right? Now you will see that this element is greater than this element. So you update the next greater than value of this element as 8. You pop this. Now you check the stack top again. You check that this particular element is also less than 9 comma 8. Hence you update the next greater element of the 5th index as 8 and pop this. And you again repeat the process. So you will update this as 8 and you insert 9. Okay, so I hope what is happening is clear by now. But like, why is this giving you the correct answer is may not be very clear. Okay. Now let's just talk about the intuition for this algorithm. So basically what you have is, so if you see this 8, this 7, and then you get this 9. Now if this 9 is a greater than the next greater than element of 8, then it should also be the next greater than element of 7, right? And similarly, if 9 is not the next greater element of 7, then 9 cannot be the next greater element of 8, right? You will, if you have this stack 8, 3, 8, 5, and 7, 7, and then you come across this element 9, 8. Then the fact that this is in the stack top means that the next greater element is not yet found for this particular element. Because you see that whenever the next greater element is found for a particular element, you pop that element from the stack. And this particular value is in the stack and this particular value is the current element, means that this is indeed an element that occurs after this element and has a greater value. So this must be the next greater element for this value. Now once the next greater element for this value is found, you just forget about this element by popping this. Now you check that, well, so 7, 7 was here. So now you erase this part. I'm not physically erasing this part for a reason. And after popping this thing, you will just check if 8 is less than 9. Well, that means, so if 8 is less than 9, that means that 9 can be the next greater element for 8. And all the other elements that were above this value that may have been pushed and popped subsequently must have a value that is less than or equal to 8. So that is why this is called a monotonic stack. So for example, this particular value, this is a sorted, this particular stack maintains a sorted order, right? So if anything that comes above this line will have a value that is less than or equal to 8. But since you have a 9 over here and you have popped this value, then you can say for sure that 9 is the next greater element for 8. So you can basically update the next greater element of the 5th index as the 8th index. And then you, okay. I think this can still be a pretty confusing explanation of this particular, for this particular sequence. So let's just take another sequence. Let's take something like 6, 5, 4, 3, 2, 5, 7. Okay. Now what happens is, if you keep a stack, the first element that you will be inserting is 6, 1. The next element you will be inserting is 5, 2. You won't be popping this because this is not less than 5. And similarly, you will be pushing all the elements through this particular value. 4, 3, 3, 4, 2, 5. Right. Now you will notice that this particular value 5, 6. 3, 4, 5, 6, 7. So 5, 6 is greater than this thing. So you will just update the next greater element for this as 6 and pop this thing. And you will continue the checking. So the next iterator element for this thing is also 6. The next iterator element for this thing is also 6. And now you see that this particular value is not strictly less than this particular value. So you stop there and you push 5, 6 into this particular stack. Now the next particular pair is 7, 7. And you see that, well, this value is 5, 6 is less than 7, 7. And so you again, you check, you update, you pop. Then push this value. Now, what happens is everything gets, so this particular loop ends, but there can still be some elements in the stack. Now the elements that are left in the stack do not have any next iterator element, so you can blindly put -1 for all of these. So this completes the entire algorithm. I hope it's clear to everyone, right? So I'll just, while s dot, while not s dot empty, so you are assigning the next of the s dot top to be -1. And you're popping this value. So even if this particular algorithm is not like super intuitively clear, then I guess you can try running a few more examples. That would be helpful. Otherwise, if it's more or less clear, we can move on. So can someone so does anyone have a serious problem with this algorithm, or is it more or less clear what we are trying to do?
Yeah, I have a question.
Okay.
Why do we storing this value? We can also store the index value only.
That makes sense. That makes sense. You can only store a stack of indices and then check A of the stack index and then do it that way. But over here, for demonstration purposes, so if this value is visible in the stack, then it's easier to show that this value is less than this value and this value is greater than this value. Yeah, so if you are choosing to keep a stack of only indices, and then you can do something like stack int s, then you need this will totally work. Any other doubts regarding this problem? Okay, I hope so it's more or less clear what we are doing. So I'll just recap it once more. So we are keeping a stack of elements whose next greater element is not yet found, and then when we are finding an element which is greater than some of these elements, we are removing these elements from the stack and updating the next greater than value. I hope this is clear. Again, does anyone have any serious questions regarding this problem? Okay, I'll assume that it's more or less clear and move on. I mean, it's a very classical problem. If something's wrong, you can also Google this thing, or maybe you can, if you find it difficult to understand even after a couple of tries, then you can maybe contact me. Okay. So let's move on to the next problem. So this problem is often referred to as a sliding window minimum or minimum element of all k-sized windows. So what this says is you need to choose. So you are given an array array A of n elements, and for all windows or like basically subarrays of size k, find the minimum element. So for example, in this sample data, I've taken k equal to 8. So the first window of k equal to 8 is this particular window where the minimum is 2. Then you can move this, you move this window by 1 and the minimum element is still 2. Then you again move this element by 1, the minimum element is still 2. Then you move this element by 1, it's again 2. Then you move this element by 1, and now you observe that the minimum element in this window is 3. And then you move this by 1, and then you see the minimum element is again 2 and again 2. Okay, so I hope the problem statement is clear. So you need to output this particular value, or if this value was something like 7, then this answer would be a bit different. So the answer would be same up to this point. Then when we move the sliding window by another step, the minimum would be 5. And after the next movement, the minimum would also be 5. Okay, so is the problem statement clear, everyone?
Yes.
Okay. It's okay. So someone tell me the brute force solution quickly for this problem. Order
So it will be, I think, we can first of all iterate over all the indices till I minus k, sorry, length minus k, and then we can directly use the
or I
function
from
of the minimum.
0 to n minus k, something like that.
Yeah, then we can directly use the function of finding the minimum.
Okay, you can find minimum element of this thing, right? An element of, I think you can do something like a of I, a
Yeah.
plus I plus k, I guess, right?
Yeah.
So what will the complexity of this particular algorithm?
It will be k into n.
K. Right. So this is the brute force solution. Now let's optimize this solution a little bit using set or multisets. So given the spoiler that we will be using multisets or sets, can someone come up with some solution? Anyone? Okay.
Can you explain multiset? Because I forgot about it.
Okay. So you remember sets, right?
Yeah, I remember
In
set.
multiset, basically duplicate elements are also allowed. In sets, you don't allow duplicate elements to be stored. In a multiset, you just allow duplicate elements to be stored. That's it. Okay. I think I'll. Is there an echo? Hello. Okay, using sets or multi-sets, what we can do is we keep a set of all the elements that are in the particular window, and then we move to the next element. To the next window. We remove this element and we insert this element, and then we can just find the minimum of a set. So, does anyone know how to find the minimum of a set? I think we need this. Sorry. I'm hearing myself a lot. Okay, is someone trying to say something? Okay. Okay, I think people might already know the solution to this problem. So what you do is insert the first k elements in a set. K elements in a set. In a multi-set, let's say. Multi-set. The set of int, let's say, or long run. Yes. Then you do the following for I from k to n. So I'll be assuming the integers, so the array is one indexed. So from I for I from k to n, you print the minimum element in the multiset. So how do you print the minimum element in the multiset? You just print the value of s dot begin, right? The beginning element would be the minimum element. And then if I is less than n, so what do you mean by what does this mean that I is less than n? Well, the window is not the last window, so it's somewhere in between. So if I is less than n, then we move this window to the right by one step. So what has to be done regarding this? So I plus 1 has to be included in the set, and I minus k plus 1 has to be discarded from the set, right? So let's just number this for our convenience. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is I plus 1 has to be included in the set. And I minus k plus 1 has to be excluded from the set, right? So if I is less than n, s dot insert ai plus 1, s dot erase. So this part is a bit tricky for multi-sets, since you want to erase only one occurrence of this particular value. S dot erase, s dot find a I minus k plus 1. This part is this algorithm is here, right? Is there any problem regarding this algorithm? Yes, no, still confused.
No, it's clear.
No,
It's clear.
Sure. Okay, let's move on to so what about the complexity of this particular algorithm? We go off.
And login.
n
And
minus
log,
k.
okay, and log k, I guess, right? Yeah, I think this is the complexity. because these operations, so the set is of size k at all times. So these operations are log k, right? This is fine, right? Okay. Now moving on to a solution with what we call a monotonic. So what is a monotonic queue? Well, it's a very specific data structure that we implement using a doubly ended queue, which can handle this problem, right? So to understand the monotonic queue approach, okay, let me copy paste this thing. Can I copy paste? Yeah, so this is copied already. Okay. Now the first observation. So if you have a particular window of size, let's say this particular size. So what is the minimum element of this window? Anyone?
2.
Two, right. Okay. Now the observation is that all elements that occur to the left of this 2 and are greater than 2 can never be a minimum element of any other window to the right of this window, right? So, for example, when this 2 is your minimum, neither 8 nor 5 nor 4 can be the minimum, right? Similarly, at some point of time, this 5 can be the minimum for some particular window. But if this 5 is the minimum for some particular window, this 8 cannot be a minimum after that, right? Why? Because let's say you have 5 and 8 over here. So for any window that contains 5 and 8, the minimum will always be 5 or something that is less than 5, right? So all the windows for which 8 can be the minimum must not include 5, right? And similarly must not include 2 as well. So putting a bit more structure to what we just said, we can have this particular claim. So if you are in a window and you choose any particular number in this window, all the numbers to the left of this particular number that have a value greater than this particular number can never be a minimum in the subsequent operation. So this 5 exists, this cannot be minimum, this cannot be minimum, this cannot be minimum, right? Similarly, this 2 exists, so this 8 cannot be minimum, this 5 cannot be minimum, this 4 cannot be minimum. Is this particular observation clear? Okay, so I'll be rephrasing the observation a little bit differently. So all the possible candidates for your minimum, so if a possible candidate for your minimum has an index I, then it must be the case that in the current window, there is no j greater than I such that aj is less than ai. So in the current window, check that 8 is not valid, because if you consider 8 as I, then there is j equal to 3 as I, such that ai is 8. Then you see that there is j equal to 4, which is greater than I, and aj has a strictly less value than ai, right? So you can exclude 8. Similarly, you can exclude this 8 because this 5 exists. Similarly, you can exclude this 5 because this 2 exists. Similarly, you can exclude this 4 because this 2 exists. But you cannot exclude this 5 directly, right? Is this particular observation clear? Anyone? Yes? No? Still not clear?
I think it is clear.
Okay. Okay, now if this is more or less clear, can you tell me the nature of the candidate values that you have? So let's say here you have 2, 5, right, as the candidate values. But you can also have something like 1, 2, 3, 7, 5 in your current window. Then can you tell me what are the candidate values? Just check that 7 is the only value that is not a candidate value, right? Because if you check for I equal to 1, we'll check that there is no j greater than 1 such that aj is less than ai. So 1 is perfect. 1 is a valid candidate. Similarly, there are no elements to the right of the second element that is greater than 2. So the second element is also a valid element. And the third element is also a valid element. But for the fourth element, you see that this fifth element that has a value of 5 has a strictly less value than 7. So this makes 7 not a valid element, right? And since there are no elements after 5 in the particular window, you don't have any j such that aj is less than ai. Hence, the fifth element is also a valid element. Now you observe this thing that these particular elements occur as a sorted order, right? Can someone tell me why these occur in a sorted order? Why can't you have something like 1, 3, 2, 5?
I think because the condition that you have written itself is of sorting, because j is greater than I and we have given the condition that aj is strictly less than ai.
Exactly.
So if this
So
case, then
yeah,
it will
so
be
if
sorted order.
exactly, so for this example, this cannot be the case because uh, 3 can never be a candidate, a valid candidate value if 2 is present after that, right? So if 2 is present after that, then this particular condition gets validated. So 3 cannot be in your set. Now these two observations, that these valid candidates occur in a sorted order. By the way, as one of you said that this is the condition for sorted order, you can check something called the Stalin sort, which is a beam version of a sorting algorithm. Basically, what this does is kind of similar to Stalin sort, but yeah, it does give you something meaningful. Okay, let's come back to the problem that we had. Now, what we will do is we can maintain this set of valid candidates in a doubly ended queue, a deck. And we call this the monotonic queue. Why we call this a monotonic queue? Because this particular element, this particular doubly ended queue contains element in a sorted order, hence a monotonic order. Now, how do we maintain this queue? Well, it's fairly straightforward if you understand this observation. So if you have some valid candidates in your monotonic queue, and then you are about to move this window by one. Okay. Now what has to be done? Well, now you have encountered this 7 as a new element. Well, if 7 is encountered as a new element, you only need to check if this 7 keeps this monotonic queue in a sorted order. If this 7 does not keep this monotonic queue in the sorted order, this 7, some of the elements cannot be valid candidate elements anymore. We will see in the next 2 or 3 iterations for such cases. And you also need to take care of the fact that the first element can also be a candidate element. And if we are moving this value, then we need to pop the first element. Well, in this particular example, it's not very clear. Let's just move on to the subsequent iterations, and we will get an iteration where you will be popping the first element. Okay. So in the next iteration, what do you do? To insert 9 as a valid candidate, you check if so. After checking that this 9 keeps this set of valid candidates in a sorted order, then you push this 9 to the monotonic queue. And now these are your set of valid elements. Okay, now moving on to the next. Let's move this. Okay. So now what happened is, now this 3 was added and this 8 was removed. Well, this 8 was not a candidate element, so we don't need to worry. This 4 was also not a candidate element. Now you check that after inserting 3, this won't be sorted. This won't be in a sorted order. Now, what does that mean? Well, this means that the last element is greater than this particular value. That means this particular condition is violated for the last element. So the last element is no longer a candidate element. So you can pop the last element and mark this element as not candidate. Again, you check that this the last element, if it's able to maintain the sorted order. Well, no, because 7 is greater than 3, then you conclude that 7 is also no longer a candidate element, so you exclude 7 from your list of candidate elements. Same for 5. Okay, I think moving these things moved. This used to be this. This is a very hard thing to do. Just recross these things. Okay, I think this should be clear right now. Okay. Now you see that 2 and 3, they do maintain a sorted order. That means 2 is still a valid candidate element, right? So you can just cross out 5, but you don't need to cross out 2. Well, now the maneuver for this particular window is done. Next, you move this window by 1. Now observe that by moving this window by 1, you are removing a candidate value, right? So what you are doing, you are removing the first value that is in the candidate list. So you basically pop the candidate monotonic queue from the front. That's it. Now you insert 5. You check if 5 is uh, 5 maintains the sorted order. Yes, it does. So you move on to the next step. So you move on to this particular window. Then you check that 8 also maintains the sorted order. Then you move on to the next window. You check that 7 does not maintain the sorted order. Then you need to pop 8, mark this as not a candidate value, and then push 7. Right. So these are the candidate values. Okay. So now most of the operations are clear. So basically you can pop from front, you can pop from the back, and you can push from the back. So that is why we are using a doubly-ended queue. But we still didn't mention how to report the minimum of the particular range. Well, if these are the minimum, the candidates for the minimum values, so what will be the minimum of this particular range? Anyone? The candidates for
minimum of the candidate that way.
Yeah, and that coupled with the fact that this candidate doubly-ended queue is in a sorted order, this means that the first element itself will be the minimum, right?
Yeah.
Okay. So that is the important thing. So the first element is the minimum. When you insert, let's say some other value 4, then you pop the elements from the back until the monotonic queue is the queue is monotonic, and if you are ever required to erase a particular candidate value, you just need to pop from the front. That's it. So let's just talk about the code for this approach. So first of all, we need to insert all of the elements in the first window, right? Let's say this was our first window. So for I equal to 1, I less than equal to k plus plus I. So if you have a doubly-ended queue, something like again, we will be working with pair of long comma int. So it's just the value comma index pair. Value comma index pair. And then we create the DQ for the first k element. So for int I equal to 1 to k. Or if our DQ is not empty, and the last element is greater than the current element, that means the sorted order is getting disrupted. DQ dot back dot first is greater than AI. So you pop this AI DQ. Pop back. And this may be done multiple times. So instead of using a if, we will be using a while. Right. And then after that, we will be pushing the current value. DQ dot pushback AI command. Now we will be handling the part where we move the sliding value. less than equal to n plus plus I. So first we will report the minimum of the current sliding window. So what will be the minimum? It will be just the first element dq dot front. Something like this. Then we need to check if so you remember the part where this the candidate element was to be removed for sliding. So how do we check that? Well, we can check just by putting an if condition. If the front element is, well, if the front element is the element is the first element in the current sliding window, then we just pop the front. And then we again check if
Instead of equal, what I think it should be less than equal to, because there is a possibility that we'll be left with the element that is after this I minus k plus 1, that is towards the left. So why?
okay. Okay, so basically you can see that when, so let's say when the window was this particular window from 4 to 9, and then you want to move the window from 5 to 10. Now you know that the candidate elements are from the current window, and in the next window there is only one element that was from the previous window but is not in the current window, right? So that element is 2, 4. Correct.
Yeah.
Okay, that means that the only element that has a chance that it will be it can be removed is the first element of the previous window. So that means the index of that element must be I minus k plus 1. So this equal to works, right? I mean, even if you do this as less than equal to, this would also work. But even if you keep this just equals, this should also work.
Yeah, understood.
Okay. Okay, so
Means the element there is no possibility of the element left with index having less than I minus k plus 1. It will be removed previously only if it is in the candidate list.
yeah, exactly. So if it was to the left, so if this was your candidate value at some point of time, this would have been removed when your window shifted from this to this, right? That was already removed before.
Yeah.
Okay, I hope this part is clear. Okay, so I'll just briefly write the remaining part. The remaining part is basically the same as this particular part, while the next element cannot be added, that is s dot empty and s dot top, s dot front. It's not s, right? It's dq. Sorry, dq dot front, dq dot back dot first is greater than ai plus 1. You just pop dq pop back, and then you add ai, comma, and this has to be done only when I is less than n, right? If I is less than n. Okay, so I hope this algorithm is clear. But well, we are at the end of this meeting, but let's just talk about the time complexity of this algorithm. Can anyone tell me about the time complexity of this problem? Well, it seems that in the worst case for each I, you can pop order k elements, right?
Yeah.
From this part. So what do you think the time complexity will be?
O
Order,
of k square. Maybe. No, sorry.
order of n times k, right?
Yeah. O of nk.
But observe this thing. You push an element in the stack once and you pop that element in the stack once, right? You cannot push an element in the stack twice and you cannot pop an element in the stack twice. So if you just sum up across all push and pops, the number will not exceed 2 times n, right? So it may happen that for one particular I, there are order n pops, but that must mean that there will be many other points that will have like no pops, right? Do you understand what I'm saying?
Yeah. In the worst case, there is a possibility that we have to pop all the elements for all the k windows that will
Yeah,
be.
but the thing is, when you pop all the elements, well, when you pop some element, it can never get inserted for the second time, right? So when you're popping this 9 because this 3 exists, so this 9 can never get inserted, right? So basically, if you sum up over all pushes and all pops, each element can be popped exactly once, and each element can be pushed exactly once.
Yeah. It
So
will be.
the total, yes, so
Yeah.
the total complexity would indeed be order n, right? Not order n times k. Is that clear? So this is called uh, this way of analyzing time complexity is called the amortized analysis of time complexity. So instead of looking at each step, we look at each element. This element can be popped once and pushed once. This element can be popped once and pushed once. This element can be pushed once and popped once. Right. So for each element, this can be pushed exactly once and popped exactly once. So the number of operations would not exceed 2n. So the entire program would run in order. And similarly, we didn't talk about the time complexity of the stack algorithm for the same reason. Each element is popped and pushed exactly once. So the time complexity for this is also ordered, right? So is this part clear?
Yeah. It is clear.
Okay. Okay, so I think we should stop discussing right now. It's already 7:30. So is there any doubt regarding anything we have covered till now?
Can you share these slides?
Yeah, I'll share the slides. Okay, so I hope everyone's. So these are these are classical problems that are uh, done using these data structures, and this discussion was just a demonstration on how to do it using C++ STL. But I think you can also extend these solutions to other languages like Java and Python as well. But yeah, in CP we mostly use C++. That's it. Okay, so any other questions slash suggestions slash comments? Okay, I think I can stop the screen sharing. No? Okay.